think it's recording. Sometimes it crashes on me, but I think it's good. Okay, so next week, it's 9th week. Can you believe that? It's like the quarter is gonna end, and okay. So next week is our last class. We're gonna have our final exam here, and I posted this exam question pool. All right, so I think there's like, I don't know, how many questions did I put on here? I was trying to think of questions that I can put. Okay, so there's 24 questions on here. I'm just gonna draw like 8 questions or something from the pool, and then you'll just write your answers down. I don't know. I tried to do mostly a conceptual focus. A few of them will require some calculations just to kind of, because I couldn't think of how else to test your conceptual understanding without a few calculations. So bring a calculator, and then, I mean, you can practice on these problems, and that should be it. I'll be on campus this Saturday. I'm on campus pretty much 5 days a week, so if you have questions, you can try to set up an appointment. But I'll be on campus on Saturday. And what did I say for the review session? Okay, so I'll say 6 o'clock. So Saturday evening, I'll be on campus, and so you can come to office hours at that time, or if that's not convenient, you can join 6 p.m. Saturday. You can join via Zoom meeting. This is you just download the program, and then I don't know, it's like a web conference, okay? And then you can ask questions that way. And then I think it has a record feature as well. So I'll try to record it, and I'll post a video of that as well in case you're not able to come during that time. Obviously you won't be able to ask questions, but you can see what other questions, what questions other people ask. They should be back there, yeah. And so anyway, that's that. Are there any questions about the final? Okay. I'm gonna get in touch with Jake about homework grading, and I know we're like super behind there. And then I've also been really bad about taking attendance, so I'll probably just throw in like empty patter things and stuff like that. Okay. Don't worry too much about your grades, okay? I mean, study for the final, of course, okay? Study for the final and do your best there, but, don't, if you do that, we should be okay. Just don't turn in a blank final. That would be bad, okay? Blank final, bad, okay? But study, if you've got the question pool. I'm trying to be nice to you guys. No surprises here. Okay. Any other questions? I hope you feel like you've learned stuff and at least been exposed to different concepts. I know we're covering a lot of stuff at just a shallow depth, but just to kind of provide some exposure to like kind of the stuff that you might be doing, and not to say that like, and then there's so many topics that we can only do so much in 9-10 weeks, and so future classes might cover some of this stuff in greater depth. They might cover entirely other stuff that we haven't gotten to. So but at least a little flavor and taste of what's out there. Anyway, so I hope you liked the class. I think I don't know if course evaluations have been activated yet or not. I think that comes soon, and I appreciate your reviews, and I hope I've I hope you're willing to give me high marks, but you know, I will eventually read all of your comments and suggestions after grades are submitted and everything. But I hope you've liked the class, and yeah, and I'm always open to hearing any comments or suggestions on ways to improve the class as well. Okay, so today we'll continue looking at Bayesian statistics with Monte Carlo methods. And so last week we kind of introduced the topic of Bayesian statistics, and we said the key idea for Bayesian statistics is that we no longer treat the unknown parameter as a fixed value, okay? We treat it as a random variable, and so the only way we can kind of express what we know or believe about the random variable is with a probability distribution, okay? So now, rather than just saying we think the proportion, so if we go back to our example where there's a pouch, and inside the pouch we've got red and blue marbles, and we're not sure how many, and we want to estimate what proportion is red, rather than just saying there is a fixed value here, we're going to say the proportion that's red is some unknown quantity. And we represent that with a probability distribution that goes from 0 to 1, because that proportion red can be any value between 0 and 1. And so there's infinitely many values, and so we represent that with a continuous distribution here, okay? And so, you know, we might observe data, and, you know, the data, maybe we say we draw 20 marbles with replacement, and we see 14 red marbles and 6 blue marbles, okay? And we'll say prior to looking at the data, we'll say we have no idea what proportion is red, okay? It could be anything from 0 to 1, and we're going to say all of those are equally likely. So we've got a uniform distribution. And then once we see some data, we see 20 marbles, 14 are red and 6 are blue, you know, that's 70% red. You know, if we did maximum likelihood estimation and had a single point estimate, we would say 70% is our guess, okay? But here in Bayesian statistics, we don't want to say it's a single value. We want to say that there's a range of values that that proportion could be, okay? And so we express that using a beta distribution, and I quickly just went through a little bit of math here, and I said, you know, the likelihood is in this form. It's a uniform distribution, which is equivalent to a beta 1-1 distribution, which is p to the 1 minus 1 and 1 minus p to the 1 minus 1. So basically, p to the 0 and 1 minus p to the 0, which is just going to be 1, okay, which is the uniform distribution. And then the likelihood for our data is p raised to the 14th power and 1 minus p raised to the 6th power. And when you combine that, you'll get p raised to the 15 minus 1 and 1 minus p to the 7 minus 1. So that gives us a beta distribution with parameters 15 and 7. And when we graph that, this is what it looks like. So this tells us that, yes, indeed, as we would expect, if we see 14 red out of 20 marbles with replacement, that indeed 70% is our most likely guess, okay? And but other values are also possible. Maybe it's as low as 50%, okay? Maybe the proportion that's red is 50%, and we just happen to draw a few extra red marbles, okay? That's certainly a possibility. And so with that in mind, we might want to answer a future question. Someone could say, all right, if I go into the pouch and I draw 6 marbles, what's the probability that I get 4 red ones, okay? And if we had a single estimate of p, then that's easy. That's just a binomial probability. We do 6 choose 4. p to the 4th power and 1 minus p to the 2nd power, okay? That's easy to do if we know exactly what p is, all right? And so if p were equal to 0.7, we could just use the computer and do d binom. 4 size of 6, p probability is 0.7, and we get this number 0.324, okay? But again, we are in Bayesian statistics, we don't treat it as a single value, and we say p could be any value between 0 and 1. 70% is most likely, but 60% is likely, 80% still pretty likely, and we want to consider all of these things, you know, 65% is even more likely and stuff like that. We want to consider every single possible value of p. And so to do that, we would weight each possibility of p by its probability, okay? And so we have the function h of p. H of p represents this quantity that we want, okay? It's the probability of getting 4 red out of 6 draws if for a particular value of p. And then we have f of p, which represents this distributional curve, which says these values of p are more likely and the other values of p are less likely. Okay, and so this integral is kind of messy, right? So h of p, which is the probability of getting 4 red marbles out of 6 draws, is 6 choose 4, p to the 4, 1 minus p squared. And then the function that represents the beta distribution with shape parameters 15 and 7 is this, p to the 15 minus 1, 1 minus p to the 7 minus 1, okay? So, and we would compute this across every single possible value of p, which goes from 0 to 1, okay? So for every possible value of the proportion that's red in the bag, we're going to compute this, all right? And so this is an integral from 0 to 1. That's what we do, all right? So h of p represents the function we would use if we knew the value of p, and then f of p represents the probability density function, in our case of beta 15.7. So this is technically, like we can solve it analytically. It's not an intractable integral, but we can see it would be pretty messy to do, okay? Because you'd have a 1 minus p. Eventually, if you combine all the terms, you would have a 1 minus p raised to the 8th power, and you'd have to expand that out, and you'd integrate that polynomial. But in other cases, sometimes we get intractable integrals. We get integrals that we cannot solve mathematically, okay? And so in those cases, we would do we can do Monte Carlo integration, okay? And so this is, we're entering, I guess, this huge realm of Monte Carlo methods, okay? And again, you can take an entire course on Monte Carlo methods, and we get 1 lecture on it. So, and the idea behind Monte Carlo methods is that instead of trying to do hard math, we're going to use basically computer-generated randomness to help us get an estimate, okay? Monte Carlo methods are not able to produce exact values, okay? That's one thing that's important to realize and recognize, is that you're not going to get exact values. You're going to get an estimate, but maybe that's all you need, okay? And so basically, this is what we want to, right? So if we look at our function, we've got the integral from 0 to 1 of h of p times f of p dp, okay? Here I just kind of use the generic random variable x, and I'm using the notation from George Casella. And so, so anyway, with a Monte Carlo integration, and it's written in the handout, but I kind of want to just label all of these things. All right, so we've got e of h of x I don't know how to So this thing, this is the expected value of the function h applied to the random variable okay, so it's the expected value of the function h applied to the random variable x, where x, and this is the funny part, but where x, the random variable x, is defined by the probability function f. Okay, so this is saying you've got some random variable x that's defined by some probability function. Maybe it's the uniform function, so it's just one. Maybe it's a Gaussian function. It's some kind of probability function, all right? And so in our case, because our posterior distribution of P is a beta distribution, then RF is going to be the beta distribution 15, 7. So it's all right, and this thing, this is equal to calculate this. So the expected value of h of x, okay, where x is defined by f, is equal to the integral equals the integral over the entire domain of x That's what this part means. Okay, the integral over the entire domain of x of h of x times f of x dx. Okay, integral over the entire domain of x of h of x times f of x, which is the PDF. Okay, dx. So h of x is the function, and the PDF, okay? So if you just wanted the expected value of a probability distribution, what would your h of x be? Your h of x would just be x, actually, okay? So like, so if you just want the expected value of a PDF, then h of x is just x, okay? And because you'd have the expected value of x is equal to the integral of x times f of x dx, okay? And this is kind of how we just write it, but you might throw in this little f, right? So if we expected value so where's the continuous case? Now, countably infinite expected value, okay, yeah. So expected value of x is x times f of x dx, right? So if you just want the expected value, that's what you have, okay? All right. And if you want the variance, where do we get the variance? I'm not going to find it in the that will just be this, x minus mu quantity squared, okay? Your h of x will be x minus mu squared, f of x dx, okay? So, okay, and then you get the variance of x is equal to the expected value of x minus mu squared of the integral of So anyway, that's what you have, right? Okay. So this is how we define the variance of x, and that's exactly what we have. Okay. So whatever function it is, whether it be things you are accustomed to seeing, like the mean or the variance, okay, or in some other case, what did I say? We want I don't know, the probability of getting 4 red out of 6 draws, okay? We just have to define our function h of x and then multiply by f of x and take the integral across all possible values, okay? But that integral is quite messy, and so we can do Monte Carlo integration, okay? So this is what we want to do. So for Monte Carlo integration, all we have to do is we generate a whole bunch of random values drawn from the probability distribution f, okay? So in our case, our f is the beta distribution with parameters 15 and 7, and here we would just generate like 1,000,000 values from the beta distribution with parameters 15 and 7, okay? And then you apply the function h to all of those random values that you've generated, and then you take the mean. Right? And that's it. Okay, it's very simple. Okay, and so here we have a random distribution generator, or a random number generator for the beta distribution. So it's very easy. All we have to do is I'm going to just say random p is r beta. So r beta is the function that will generate random values from the beta distribution. And I say I want 10 to the 6, or I want 1,000,000 values here. My parameters are 15 and 7. Okay. And here the function h, I'm going to call it, I'm defining a function p, which is really just calculate the binomial probability with parameters 4, 6, and p. Okay, so this is our function. And all I do is I just apply h to those random values p, and I take the mean. And when I do that, my estimated value is 0.2894149. Okay, and again, just to kind of show that this is an estimate and not something exact, I'm going to do the exact same code, and I just change the seed from 1 to 2, and I do the exact same thing, and I get a very similar but different value. Okay, so my first time I got 0.2894149, and here I get 0.2894684. Okay, but we have agreement at least for the first 4 decimal places. Okay, so we're off by less than 1/10 of a percentage point. Okay, but these are pretty different from using just the single point estimate. Okay, if we said the probability is 0.7, then our value would be 0.324. Okay, and so here with our beta distribution, we're getting something quite different. Okay, and I just kind of want to show that if we generated a whole bunch more data, right? Like if instead of drawing 20 random marbles from the pouch, if I had drawn 20,000 marbles, okay, and in the 20,000 draws I get 14,000 red, then I could be a lot more confident that the proportion in the bag is 70% or something very close to 70%, right? And so if that's the case, then my my beta distribution, resulting beta distribution would be 14,001 comma 6,001. Okay, that would be the resulting shape. And this is what our posterior distribution would look like. Okay, so we have a very tall spike centered at 0.7, okay? But also acknowledging, you know, it could be 71%, it could be 69%, okay? We're pretty sure it's very close to 70%, but it could be a little bit higher, it could be a little bit lower, and that's what we've got here, okay? And so here, to do Monte Carlo estimation, I generate another million random p-values, okay? And if I take the mean there of those million random p-values and I apply the function h to it, you know, my estimate is 0.3240905, okay? And the estimate using 0.07 as the single value is 0.3241135, okay? So we get, so these two values are you know, very close, because here we're saying that p is going to be 0.7 or something very, very, very close to it. So our estimate's off by only just a tiny bit there. Okay, is that all right? So so here I wrote some notes. I said Monte Carlo integration works because the original integral weights each function value, h of p, whatever that function is, with the probability of seeing that particular value p, okay? You know, using the density. And so when we do Monte Carlo integration, rather than trying to like multiply the function h with the density f, we just draw a whole bunch of values from that density. And this is naturally going to produce more values of p where the density is high and fewer values of p where the density is low, okay? And because of that, because we're going to see a lot more values, so we're going to see a lot more values of p around 0.7 and hardly any values where p is 0.6, because of that, when you take the average of h applied to those values, it's naturally going to kind of weigh them according to the density of p, because those p values are going to show a lot more frequently, and then the other p-values are going to show a lot less frequently, right? If you're using conjugate priors, then your resulting posterior distribution in Bayesian statistics will generally be an easy form to work with, right? So, you know, here's the example where our prior is beta and our likelihood is from the binomial or Bernoulli, and so the resulting posterior distribution is also a beta, okay? And that's why it's very easy for us to sample values from the posterior distribution, okay? Because again, when we do our Bayesian methodology, we're going for this, right? We want the integral of h of p times f of p, and this f of p represents our posterior distribution. So whatever that is, we're going for it. So if you're using conjugate priors, it's very easy in R because we've got ways to generate random values from all of these specified distributions. Okay, so if you've got, if you're using any of the conjugate priors, you know, you define your prior distribution using a beta, and you know your data comes from a binomial. You know, you get your posterior distributions this way, and then and you can draw samples from that, right? With a gamma prior and Poisson data, then you know your posterior distribution looks like this, and you use that. Okay, and so all of these are prior distributions that already exist in R, and R is able to generate random values from all of these things, right? So if you're not quite sure about like the normal gamma, I think that exists. So you just ask R normal gamma distribution. normal gamma distribution R. Okay, so maybe you need a package to do that, okay? But a lot of these things exist, right? And then let's see, normal inverse gamma distribution in R, sampling. Wait, this is normal, okay. But anyway, most of these things, some kind of function already exists in R to generate random values from it, okay? And so doing Monte Carlo estimation or Monte Carlo integration is quite straightforward. You just need to figure out your function h, and then you draw random values from that random distribution that represents your posterior beliefs, and then you apply the function to those random values, take the mean, okay? It almost seems too easy, just these 3 steps, but these give us very good estimates. Okay, and that's kind of the it's almost too easy that we don't realize how amazing it is, because trying to do the math can be incredibly hard, all right? Okay, but there are some situations, or there might be many situations, where we do not have a random number generator for the resulting density function. Okay, so if you're not using a conjugate prior, okay, which often is can happen a lot, okay? If you're not using a conjugate prior, or your likelihood function is not something that lends itself so nicely to one of these forms, then we might not have there might not be a function in R that generates values from this probability distribution. Okay, and so we still want some way to do our Monte Carlo integration. We still want to be able to do this. We want to be able to generate thousands of values drawn from the probability distribution. Okay, because we can get a good estimate just by applying the function and taking the mean. But maybe we don't have a way to generate that, okay? And so for that, I have to introduce this topic of Markov chains, okay? And Markov chain Monte Carlo is another way for us to generate random values from some distribution without needing this, without needing to have like a nicely behaved probability distribution, okay? So when you have a nicely behaved probability distribution, just use R's built-in functions. That's great, okay? But there's a lot of situations where we don't have a nicely behaved probability distribution, or we don't even know what it looks like. And so in those cases, we have to do a Markov chain, okay? And so, all right, so a Markov chain, let me just kind of emphasize that, right? So if f of x in, if this is the thing, expected value of h of x okay, if f of x in this is a known distribution, just use R's random number generating functions. All right. I teach a undergrad class on Monte Carlo methods, and we spend a lot of time learning how to build our own random number generator functions for these basic distributions and stuff. But for you guys, I'm going to say just use R's thing. You don't need to worry about how R's function works, okay? It works, that's great, all right? We don't need to dig into exactly what's going on here. All right, so that's what we do. Okay, but if f of x is not, quote, nicely behaved, okay, then we can turn to Markov chain methods. Okay, so a Markov chain is basically kind of a simple rule set that just says, you start at this state, and then you might transition to a different state. Okay, and so and the probability of the next state only depends on the current state. Okay, so you might start off at A, and then maybe you transition to B, maybe you transition back to A, or you just transition between these different states. And what makes it a Markov chain is that where you go next depends only on your current state. Okay, what happened in the past prior to your current state doesn't matter and has no influence on what's going to happen next. So that property is sometimes called memorylessness, in that it only matters where you are now and not what happened in the past. Okay, and just where you are now is going to determine, or not determine, but give us the probabilities of where we're going to go next. Okay, and so in the kind of a finite number of possible states, we'll have a state transition matrix, or we might just call that the transition matrix. And if you've got infinitely many, you'll have a transition kernel or transition function. Okay, and so here I'm going to just start with the simplest example, a two-state case, and I draw my Markov chain possibilities diagram like this. Okay, so there's state A and state B, and if we're at state A, we might transition to state B with probability 0.3, and if we're at A, we would remain at state A with probability 0.7. Okay, and then likewise, if I'm at B, I can transition to state A with probability 0.4, or I would remain at B with probability 0.6. Okay, and so the transition matrix would be drawn this way. A to A is 0.7, A to B is 0.3, B to A is 0.4, and B to B is 0.6. Okay, so this is our transition matrix, and here I just enter that in R, and I say 0.3, 0.7, 0.3, 0.4, 0.6. Okay, so this is my transition matrix P. Okay, and so this just kind of iterates all of that. And so if we start with some vector to represent the distribution at this exact moment, we could use, we can say there's 100% of people are at state A. Okay, and so our vector is going to be represented by 1, 0, to say there's 100% probability of being at state A, 0% probability of being at state B. And we're going to just call this step 1. Okay? And so if 100% are at state A, and we go through one transition, then of that 100% at A, 30% will go to B, and 70% will remain at A. Okay? And so, and then we had, there's nothing at B, so there's nothing that goes from B to B and from B to A. So after one transition, we would have 70% at A and 30% at B, okay? And we can get that just by doing step 1, doing matrix multiplication times P, okay? So maybe this is worth drawing. So I've got A, I've got B, we can go from A to B, A back to A, 0.3, 0.4, 0.6, and 0.7, okay? And so here, I would say 1, 0, and I've got 0.7, 0.3, 0.4, 0.6, Okay, and so when I do the matrix multiplication, I'm going to get 1 times 0.7 plus 0 times 0.4, and that gives me 0.7. And then here I have 1 times 0.3 plus 0 times 0.6. And so that gives me 0.7, 0.3. And if I then apply the transition matrix from there, okay, then that means I've got 70% at A. So in kind of our next iteration, I've got 70% at A, and I've got 30% at B, which means going from here to here, I'm going to have basically 0.21, 70 times 0.3, and then going from here to here, I'm going to have 0.49, 0.7 times 0.7, okay? And then from, maybe I'll color this in blue, from our 30%, I'm going to have 0.18. 60% of this 30% will go from B to B, and then 40% of this 30%, so that's 0.12, will go back to A, right? So I'm going to have 0.7 times 0.7 plus 0.4 times 0.3, or 0.3 times 0.4. So when I do that, I'm going to get 0.49 plus 0.12, so I have 0.61. And then over on this side, I got 0.7 times 0.3 plus 0.3 times 0.6, which gives me 0.21 plus 0.18, 0.39. So after 2 transitions, I would have a distribution of 61% at A and 39% at B, okay? And we can keep applying the transition probabilities accordingly, okay? So I just do step 2, which is 0.7 times 0.3, and I multiply that by transition matrix P, and I get 0.61 and 0.39 exactly as we saw earlier. All right, so there's something called ergodic theory, all right, which kind of applies to all of this stochastic process and dynamic systems and all of that stuff. As far as Markov chains go, I mean, I think you'll cover a lot of this stuff in, I think, another later course. But kind of the important takeaway for us is that there's something called a stationary distribution, right? And if a Markov chain is irreducible and aperiodic, then the Markov chain will converge to a stationary distribution, okay? The stationary distribution is the distribution where after you go through a transition, so you apply the transition matrix P, you end up with the exact same distribution that you started with, okay? So basically in our case, the stationary distribution is the situation where, here you've got A and you've got B. And if we could quantify exactly how many are going from A to B and how many are going from B to A, the stationary distribution is the distribution where these two kind of quantities are exactly equal. So people are moving, but the amount going from A to B is exactly equal to the amount going from B to A, right? And when that's happening, then we're at equilibrium, okay? We're not, the relative sizes of A and B are not changing, okay? They remain the same, and that would be the stationary distribution. Things have kind of settled out where, there's still stuff flowing, but you know, we're at equilibrium. So you can kind of, I don't know, I guess these dynamic systems are used to model like air particles and stuff like that, right? Like they're flowing around, but you know, in this room, well, I don't know, I guess air is coming out of the vents, so you know, we might not be at equilibrium, but you know, in general, if you know, if you've got something and it's you know, things are staying steady. So that's what we have, okay? And so this can be represented by saying you've got a distribution pi such that pi times the transition matrix P equals back to our original distribution pi, our stationary distribution, okay? And so in our case, our stationary distribution for the transition matrix is 4/7 and 3/7. And so my stationary distribution looks like this. And then when I multiply the stationary distribution times P, I get the exact same thing back, okay? Here's some very informal definitions of what it means to be irreducible and aperiodic, okay? Irreducible just means it's possible to get to any state from any other state, okay? A path just needs to exist, and you know, none of your paths can be dead ends. So irreducible would be something like you got A and B and C and D, and yeah, this is fine, okay? And okay, this would be irreducible, right? Because there is a path to get to D from A, okay? And everything. It's not a direct path, but a path exists. Okay, so it's possible to transition to state D eventually, starting in state A, okay? And I mean, you could add other stuff. All right, so not irreducible is if you have, like if you've got something like this, so here you can't, no path exists to go from C to A or D to A. So this is not going to be irreducible. All right, so that's irreducible. And then aperiodic, technically, okay, so periodic means kind of like only certain values will appear at certain kind of time intervals. So if you have like this would be periodic because it would go A, then B, then A, then B, then A, then B, okay? And if you started on A, you're only going to get state A on the odd transitions, okay? On the quote odd time intervals. Aperiodic basically means that doesn't exist and you can get anything on any state, and practically speaking it just means if you can kind of go back to yourself, then this is possible and this is possible. Okay, and so you can get A on either odd or even states, okay? odd or even time intervals. Okay, so if a chain is irreducible and there's one place that double backs can return to itself, then the entire chain will be aperiodic. Okay. And at least one state can go back to itself, and the entire chain is aperiodic. All right, I don't know, maybe I'm emphasizing this ergodic stuff too much. Okay, so the point of this is that if we can get a Markov chain if a Markov chain is aperiodic and irreducible, then the Markov chain will converge to a stationary distribution. So here I have an example where we start off with a state where 100% starts off at A. 100% at A and 0% are at B. And here I just update my state by multiplying the transition matrix to it. Okay, and I just say state times the transition matrix is equal to the state. And I just do this 100 times. And when I'm finished with that, we see I've converged to the stationary distribution, okay, which we found earlier, all right? Here I do it again, but this time we start with 100% at B. I apply the transition matrix to this state distribution 100 times, and we get the exact same distribution, okay? So both of these things have converged to the distribution, right? And so so anyway, that exists, okay? And then, if we didn't bother finding the transition matrix, I mean, in this case, the transition matrix is like super easy, but we could just use the rules from our diagram, and we can say if you're at A, you have a 30% probability of going to B and a 70% probability of going to A, right? And so here I just kind of implemented what a Markov chain might look like, okay? So I'm just starting off at A. I'm going to store all of my results in just a vector called results, right? And I say, do 1,000,000 iterations of this, right? And we just say, if you're at A, then draw a random value. And if that random value is less than 70%, you stay at A. And otherwise, you go to B. Okay, so that means we get a 70% probability of staying at A and a 30% probability of going to B, okay, if we're at state A, right? Otherwise, else, that means if we start at B, then draw a random value, and if it's less than 0.6, remain at B. Otherwise, go to state A, right? And so I just run this 1,000,000 times, and my resulting chain goes A, B, B, A, B, A, B, B, A, and so this is just what we get, okay? And so this is just one iteration here. We're just going from A to B, maybe hanging out at B, maybe hanging out at A, who knows, all right? And then, and here I can just say, okay, what proportion ended up A after 1,000,000 of these things? And we get something very close to our stationary distribution, okay? So our stationary distribution is 0.5714286, and just by kind of following these transition rules, okay, not necessarily applying the transition matrix, which is kind of like knowing the answer. We're just kind of following the rules. One chain ended up with 0.571, and if I ran another chain, we would get a different result, because it's just we're basically just starting here and we're just moving from here to here and whatnot, and we can see that when we let the chain run long enough, we can be confident that the values from the chain are basically reflect what the stationary distribution looks like, okay? maybe this is worth noting, is that the stationary distribution for some matrix P for a transition matrix P can be found by taking the eigenvectors of the transpose of P. Okay, so I don't know if you guys remember eigenvectors from your linear algebra days, but so again, if pi represents is a vector representing our stationary distribution, then what we have is pi times the matrix P is equal to pi, right? And the definition of an eigenvector for a matrix A is V such that the matrix A times the vector V is equal to lambda, a scalar, times the vector V, okay? Not lambda, scalar. So this is a matrix. Matrix times vector is equal scalar times vector. And so we have something very similar. We've got vector times a matrix is basically 1 times the vector, right? And so because we've swapped the position of the vector and the matrix, it turns out we have to get the eigenvectors of the transpose of the matrix, okay? By doing the eigenvectors of the transpose of the matrix, then then we'll get this result, okay? So pi is the I guess the eigenvector of the transpose of P, all right? And if P is a stochastic matrix, or what we call a, if it's this state transition matrix, then all of the rows will add up to 1, okay? So P is a transition matrix, and all rows add to 1 because it represents, if you're currently at A, then there's these probabilities that go here. And what's going to happen is that one of the eigenvalues will equal 1, okay? And that will be in pi, the vector that corresponds to the eigenvalue 1 will be pi, the stationary distribution. And the eigenvector corresponds to eigenvalue 1 is the stationary distribution. Okay. Also, what is, I forget the name of the theorem. What is it? Eigenvector theorem, only one, all positive. There it is. Okay, look at that. School is magic. All right. So there's this theorem. Of course, I'm not going to remember that. Perron-Frobenius. All right. So these guys back in 1907 and 1912. What is that? Frobenius. Okay. Perron-Frobenius theorem. This basically says only one eigenvector will be all positive. Okay, and so basically for a stochastic matrix, I should say. Okay, so if the matrix only has positive values, non-negative values, which is going to be the case with this transition matrix or stochastic matrix, then only one eigenvector will be all positive. Okay, and that's going to be the that will be the stationary distribution. Okay, you can use eigen in R. Returns eigenvectors where the L2 norm is 1. Okay, and so you'll probably need to multiply it by a scalar so that the L1 norm is 1. Okay. So let's see if I can get this. All right, so here is my transition matrix P, okay? And so if I take the transpose of P and calculate the eigenvectors of it, something happened. Okay, R just crashed. Something happened. Let's try this again. All right, so I want this. All right, so there's P. All right, so here's P, and I can take the transpose of P, and I can ask, what's the eigenvectors of the transpose of P? And so one of the eigenvalues is 1, and the corresponding vector is 0.8, 0.6, okay? And so, you know, this is the L2 norm, so if I do 0.8 squared plus 0.6 squared, you know, then I get 1. But the L1 norm, 0.8 plus 0.6, obviously is not 1, we get 1.4. So I just have to take these values and divide by 1.4, all right? So if I do 0.8 divided by 1.4, I get that, and 0.6 divided by 1.4 gives me this, all right? And that, we can see, is equal to the stationary distribution that we have, 0.57, you know, basically 4/7 and 3/7. So, so anyway, we have all of that, okay? Maybe I'll snip this into here. And this generalizes to any sized matrix. It doesn't have to be a 2 by 2, okay? So P transpose, and then the eigenvectors. Okay, so this is our first eigenvalue, and then this one will be our stationary distribution. Okay. L2 norm equals 1, but must divide by basically 1.4 so that the L1 norm equals 1, okay? Or another way of, the L1 norm is just the sum of the components, right? So, so we just want to make sure that the sum of the components are 1, so we just scale these down, okay? And then this is our stationary distribution. All right, so just so we don't lose sight of where we are and what we want, okay? The whole point of this is that we want to estimate, you know, some function, right? We want to get the expected value of h of x over, you know, where x is drawn from, this is supposed to be capital X, where x is drawn from some probability distribution f, okay? And we said if, you know, to avoid doing the integral, we can just randomly draw values from f, okay? But we might be in a situation where generating random values of x defined by that distribution f is hard, okay? So if we're not using a conjugate prior, we might be in a situation where this thing is tough, okay? And so what we want to do is we want to create a Markov chain so that the stationary distribution of that Markov chain is equal to the probability distribution of f, okay? So that's the key part of Markov chain Monte Carlo, is that we want to design our Markov chain so that if I just let the Markov chain run, okay, which is easy, okay, it's easy. You just set up kind of some rules that says if you're here, you know, you're going to move to one of these other states using these rules, okay? We don't have to figure out how to sample values independently or anything like that. We just let this Markov chain run. And if we can set it up so that the stationary distribution is equal to the target probability distribution we want, then we'll just let the chain run, take all those values at the end, and use them, and we can be confident that those values represent the target distribution, because the Markov chain will converge to its stationary distribution, okay? So that's what we're trying to do. So we want random values drawn from the distribution f. We don't know how to draw values from the distribution f, so we're going to design a Markov chain that will converge to its stationary distribution, and the stationary distribution is equal to f. Does that kind of make sense? That's our plan. Okay. So the question is, how can we set up our Markov chain so that this property holds? Okay, and it seems like an impossible task, right? Because you know, you look at, like, what does our, you know, here's our transition matrix, and this transition matrix corresponds to, you know, a stationary distribution that looks like this. And we want to say, okay, well, what's our transition rules going to be so that the corresponding distribution, the stationary distributions, this distribution I'm specifying, you know, this target distribution, okay? And that's where we introduce the Metropolis algorithm. This is something that this guy named Metropolis, you know, put his name on, and the urban legend, or I don't know, maybe not the urban legend, but just kind of the legend is that Mr. Metropolis, it's his name, actually didn't come up with the thing. It was one of his like grad students or something, but was working for him and says, "Oh, this is good," and he stamps his name on it or something, and I don't know what happened, but anyway, so there's this, and so this is how it's going to work, and I ran out of time in creating our handout, so I'll explain all of this. But we're going to say we have some target probability distribution P. Okay, this is the distribution that we want to sample from. Okay, and this is actually the remarkable thing, is that we might not know the exact function P of x. All right, but the Metropolis algorithm will still work as long as we have a function f that's proportional to our target distribution P of x. Okay, so let me come over here. So our target probability distribution is P of x, okay? And so in kind of Bayesian stats, this is often the posterior distribution. Posterior distribution of our parameter. Okay, and so maybe this is the posterior distribution of theta, okay, which is going to be theta given our data, right? And so we have the probability of theta given our data. This is what we want to sample from. And we said, well, this is equal to y given theta times the probability distribution of theta divided by the marginal probability y. Okay, so this is the likelihood, and over here is the prior, and this is the marginal. And we often said, well, this is just proportional to y given theta times the probability of theta, because we said this thing is complex and hard to find. Okay, so we're often in a situation where we just have the numerator, okay? And so we can let f of theta just be equal to this, okay? This is technically not a PDF, it's just something that's proportional to a PDF, okay? Because this will not integrate to 1, okay? Technically not a PDF because it does not integrate to 1. Okay, but this is okay. But that is okay. The Metropolis algorithm says, I just need something proportional to the PDF that you want, and I'll take care of the rest. Okay, you don't have to give me the exact thing. So the Metropolis algorithm is like perfect for Bayesian statistics because we're often in a situation where we can get the numerator, figuring out the likelihood, and the prior. That's usually not too bad. Okay, it's figuring out this marginal probability, just this constant, so that everything integrates to 1. That's often computationally not feasible. All right. Or just too much work. So we're very thankful for the Metropolis algorithm that just says, okay, that's all right. All right, and then so we've got this distribution f, or not distribution, we have a function f that's proportional to our target distribution, okay? And then meanwhile, we're going to say, all right, we don't know how to generate random values from this distribution or this function, but we have a proposal distribution. G, okay? And the proposal distribution is something easy, maybe like a normal distribution, okay? Something that we can generate values from, okay? Proposal distribution. The proposal distribution is an easy distribution, okay? One that we can generate random values from. All right, so maybe a normal distribution. It's often a common choice. Okay, and the proposal distribution is conditioned on our current value of x, xt. Okay, the proposal is conditioned on our current value xt. Right? So it could be g of x prime given xt is equal to a normal distribution where mu is equal to our current value, and maybe sigma squared is just equal to 1 or something like that. Right? So if xt, so as the function moves around, okay, as we update xt, as we draw new values for xt, we update the proposal distribution accordingly. Okay. All right, so anyway, what we do, the way it works is we propose a new value, x prime, from our proposal distribution. Okay, we say, using our proposal distribution, I was going to say, we're going to just propose a new value, and then we calculate something called the probability of moving. Okay, this is going to be the ratio between the proposed value. It's kind of small, but it's the f of the proposed value divided by f of the current value. Okay. All right, so this is our process. So we, step 1 is propose a new location, x prime, from the proposal distribution. G of x prime given xt. 2 is calculate p move, okay, which is equal to the minimum value of 1 and f of x prime divided by f of xt. Okay, so what is the probability of the proposed location versus what is the probability of the current location? All right? And what we see is that if the proposed location is more likely, okay, then f of x prime divided by f of x current. Okay, so if the proposed location is more likely than the current location, then this thing is going to be greater than 1. Okay, and that basically means we are going to go there for sure. Okay, the reason why we have this min 1 and all of this is just because the probability of moving can't be greater than 1. Okay, so the probability of moving is at most 1. And so, so that's why it says the minimum between 1 and this value. So if it's less than 1, then this ratio, then the probability of moving is equal to the ratio. But when the ratio goes over 1, then the probability of moving is equal to 1. Okay? So if the probability, then this and p move equals 1. So this means we definitely go to a proposed location if it's more likely than our current location. Okay. And on the other hand, if the proposed location is less likely than our current location, then maybe we'll go. And we'll go according to the ratio of their probabilities. Then maybe we will go, and we go with a probability equal to the the ratio of probabilities. That is, p move equals to f of the proposed location divided by the current location. Okay, and so to implement that, it's simple. You just generate a random u from the uniform 0 to 1, and if u is less than p move, then you go. And if it's not less than that, if it's greater than that, then you stay. And what that means is that if you accept the proposed value, then the next value, x at time t plus 1, is going to be the proposed value. And if you reject the proposed value, you reuse the current value, okay? So every iteration produces a new value, okay? It's just you might get a duplicate of the current value. So if you propose a new location and it is not one that you like, okay, then you reuse the current value. You don't just do a new thing. All right, is that okay? Oh man, it's already 7:30. Okay, why don't we we'll take a short break here. We'll say 10 minutes, and then we'll come back and I'll kind of code up the Metropolis algorithm here, and then we'll kind of play around with an example that I think is kind of neat. So, all right, so we'll say 10 minutes here.